Thank you, Nicolas, and also thank you, Hugo and Alessandro, for the invitation. It would be nicer to be back in Lisbon in a not regular time, but I'm very happy to meet you the same in this online occasion. So this is what I'm going to present is a recent work obtained in collaboration with Filippo Riva, who is currently a postdoc in Pavia. Okay, I will start with something that you surely already know, that is Newton's second law of dynamics. I'm sure you already know, and this is basically if you want to start modeling a physical system, this could be one of the starting point, probably. And you probably also know statics. So if you want to look for equilibria and the force is autonomous, so does not depend on time, what you do, you can set MA equal to 0, just solve F equal to 0. Also, this should be very well known from high school or even earlier. What we did today is the quasistatic approximation. So maybe probably you're seeing in statistical in thermodynamics. Some of you have probably surely worked on with it also for normal mechanical models. What is it? Quasi-static approximation. So the idea is, okay, we have an evolution problem, so we should use F equal to ma. However, it evolves slowly, so we can decide somehow that we can neglect inertia and just use F equal to 0. And this is a nice thing because F equal to 0 is clearly much easier to study. Today's topic, today's problem is, can we do this? And why can we properly do this by looking at it by a mathematical point of view? We are raising a term, and saying the system is slow, so inertia is slow is something delicate in a way. So first, let me stop sharing for a moment and give you an idea with a physical model of quasi-static approximation. So I have a marble, a metallic marble, so a point mass. I have a potential well, a glass. So if I put my marble inside a glass and I do some motion, okay, there is only an equilibrium point that is the bottom of the glass. If I'm steady, I found the equilibrium of the point of the system. Statics is very easy. If I move my glass, you can try it easily at home. The marble does not stay on the bottom of the glass. And this is dynamics. However, if I start with my marble on the bottom of the glass and I move my glass very slowly, it seems to work that I can, that the marble stays on the bottom of the glass. So why is this and what is happening mathematically? Okay. Let me go back to the slide. Okay. Let's get a more mathematical, precise description of the second law of dynamics. So A is an acceleration, and the forces, we will have several forces that will depend in generally on time. If I have an external input moving my glass, so something is dependent on time, on the state. The potential energy clearly depend on the state and on time because I'm moving my glass, and usually also on velocities. In this case, some viscous resistance to the movement of the marble. If I consider n particle, I can do the same. So in this case, I will have x will be a vector, x1, xn, with the position of each particle. And the forces, clearly, we should consider each force, all the forces for each component, but the forces might depend on the state of one particle, but also of the other particle, because there can be ever can be linked by things, for instance, or other stuff. Okay, what is the idea of quasi-static actuation? The idea, if you remember, is if I move, is to move the glass very, very slowly. So you can think of a periodic actuation of the glass, for instance, or an actuation that is a characteristic time scale. Periodicity, the period is a good time way to identify the time scale. So I'm moving my glass in a circle with a period t, or better, 1 over epsilon, moving down if my going slowly. If my time scale is 1 over epsilon, going slowly becomes taking the limit epsilon that goes to zero. So we can start again model our dynamic problem, making explicit the time scale. And again, as you saw before, if my time scale is in the actuation and the actuation is in the time dependence of the forces, at least for this kind of model, the glass, for instance. What we do is that we slow down. So we want to study how the system behave for epsilon that goes to zero. And what makes sense to look is to rescale the system in the time scale of the actuation. So we make a change variable, and this put the epsilon, an epsilon here in front of the higher order derivative, and also a component in epsilon in the velocity. And here you see already get an idea. So what we would like to study is what happens to this system when epsilon goes to zero. And the temptation would be to brutally substitute epsilon equal to zero. And this might actually work in the case of the glass. What you get to the right is exactly the static behavior. The marble is on the bottom of the glass. The left term disappears. So usually it works, and we may expect it to work. But it's not something that as a mathematician we can do just taking the limit in this way. And actually it's not a trivial limit. How do we study a limit with a coefficient that goes to zero in front of the highest of the derivative in a differential equation? So this would be the topic today. And maybe it helps also to consider some specific choice of F, some specific structure of F. Okay, so which structure of F do we consider today? As Nicolas, when introducing me, I have been working for a long time on the modeling of particular class of system crawlers. And I've done various stuff. I'm working on pure modeling, on control, on stabilization, on many topics. I always have used to the quasistatic approximation. And the reason is, okay, it is slow, and the main answer about why I can use the quasi-static approximation is it is accordance to the reality. So engineers say we can use it, biologists say we can use it. Clearly, this is the best answer, but it's not a complete answer for a mathematician. So I can do it because engineers say it's okay. Well, as you say, it's something quite delicate by a mathematical point of view. Okay, so what are crawlers? Crawlers describe a large family of locomotion strategies that we can find in several animals: earthworms, inchworms, leeches, snails. You see, they are very different. We have a longer model, continuous model, some like leeches and inchworm on the bottom right that use basically only 2 contact points. There are some difference, and strategy in the last decade, 15 years, has been imitated also by engineers with a lot of robotic replicas imitating all these strategies. So you see some more earthworm-like, some other more inchworm-like. Okay, and the other characteristic, one thing they do with this robot is that they are imitating those animals. The other thing is that they are using elastic materials in building all these examples I showed you before and many others. And this falls between a larger framework that is soft robotics. The idea is that the elasticity of the body. So the materials gives to the robot some special capability of compliance. For instance, if it is moving on irregular terrain inside an irregular interaction. Okay, by a mathematical point of view, clearly we are adding elasticity. So something else we should take into account, and it's something that complicates the problem, of course. Keep in mind, as I say, usually one describes of robots are more compliant, more delicate, again, good for patient interaction. They are also tough, and they, being elastic, have several advantages in many ways. Okay, so of the talk, it's some thought to the reverse of the usual structure. So I will start with the approximation. So how do we model cluster of body crawlers? Then we will discuss if is inertia negligible. So are they really going slow? Is the snails really slow? Is Newton really slow? And this will be, we'll do it more properly by looking at non-dimensionalization of the dynamics and then discuss what we call a food number. Then we will finally reach the theorem. So I will give you the proper mathematical convergence theory that explains why we can do the slow direction limit. And finally, we'll give you the general abstract hypothesis for the theorem. So we will work with trying to find the convergence for a specific model, but we will see that it's something quite more general. And I will conclude with some remarks and examples. So how do we model models? Well, the standard model is a chain of blocks. This is the most common one. It can be look very simple, but it's actually very effective and very widespread. So we can have a chain of blocks, each with a mass m, mi, and position xi. These blocks are linked by active links. This means is something so we have active elastic links, so they are active, so there is this part in the middle that can change its length, so we can make it expand and compress, but in the same time they are elastic, and this can seen by Addington springs. And we have some friction of the blocks with the surface. One can consider also continuous models. They are similar structure, but today we focus only on discrete one, also because for our purposes there is a relevant difference that I will tell you before about the structure of net. So mathematically, what we put in the equation. So first element, as I told you, elasticity is fundamental also philosophically for the system. So we will have the elasticity of the link. For now, we can take just a quadratic energy. So we will have, for each link, a quadratic energy that depends on the length of the links minus the rest length of the link that is actuated. So this dependence on T account for the link, the central part of the link expanding or contracting. So the total elastic energy of the model is the sum of all this quadratic energy, and look, pay attention that it is quadratic, but it's positive semi-definite because we have n masses, but n minus one links. And this is what distinguishes locomotion problem by basically everything else. We can do something more general again in the last part of the talk. The second key element is, of course, the interaction with the environment, so friction. And what the reasonable choice to consider is dry friction or Coulomb friction. One would like maybe mathematically to use viscous friction, so linear friction, because it is mathematically easier. This is not good for two reasons. One is that viscous friction will produce a continuous sliding, and this is not physically observed. Physically, you always observe some yield forces, so you need to reach a threshold force to start moving a block. And the second reason is that dry friction also introduces some non-linearity that is really useful to break symmetry. So viscous friction actually affects the qualitative behavior of the system. Okay, something more also about dry friction, and to do that is useful to see how these crawlers move. And they do basically three stuff. Probably the first you can think about is complex space change, so peristaltic wave in earthworm. So you have a contraction wave that move along the body of the crawler, or in any case, having a large number of degrees of freedom. So this contraction and expansion that they cannot simultaneously along the body of the crawler, and this is one option. Maybe more interesting for the modeling part is the second and the third one. So you saw also before, you can build models with just one link. And in this case, clearly just expansion and contraction is not sufficient. So in these cases, you can do two things. One is to produce an anisotropy equation. So here you see on the right, the friction velocity, friction force velocity law. So we have a higher friction against backward movement, and a lower friction against forward movement. And this is usually obtained by putting Bristol or hairs or scales on the surface of the model. Here you see a very simple example for CISA, but this is something else that actually happens in nature. The earthworm has also these very small hairs here that are called setae, and they produce also this kind of gripping, so anisotropic. And the earthworm does also another thing, but we will show first with the inchworm. The inchworm again has only 1 degree of freedom in the shape, so it's just contracting and expanding, but he can control the friction coefficient. So he can grip on one hand while releasing the other hand. For instance, if you grip back on the back hand, release the forward hand and start expanding, the forward hand would move forward, and then you can do the opposite to carry the forward also the back part. And this kind of strategy is called anchor crawling, and it's also has been, or inching. It has also been imitated in robots by using several mechanisms for controlling friction. And something that happens is also a combination of the last two mechanisms. And this also happens for the earthworm, and here I'm showing it for an earthworm-inspired robot. So when you have some setae and you contract your body, usually the air or the setting in the earthworm is making stiffer. So here it changes the angle, and this changes also the friction coefficient. We have a work with Antonio De Simone on CLCV, describing this as a mathematical way. So we have three locomotion strategy. Let's put everything together in an equation. So this is our force balance. So we need, inertia, the first term on the left. The last on the right is the elastic energy, and I told you before how we do it. Dry friction can be described as the subdifferential of a dissipation potential that is convex and positively homogeneous of degree 1 max. And in this case, you see we have also some control of friction in time. So we also have to add a time dependence of the coefficient, and this dependence in t, which we assume to be absolutely continuous. We can add also some viscosity. It's not a very a big deal. Actually, you can have, for instance, viscosity in the resistance to the movement of the block. You can consider viscoelasticity instead of elasticity in the links. It's optional. You can put it, you can put it for our models today, it's exactly the same. Okay, and ideally there is this actuation. Okay, as I told you before, it's a matter of time scale. All these crawlers have a periodic actuation, so both in the shape or in the dissipation potential. So we don't require periodicity, but think of them as periodic, and there is this common period in the energy and in the dissipation that is actually the period of the system. So this is the problem. What is the quasi-static problem? What is usually studied, and the system I usually refer the rate-independent system, and they're used also for other models like elasticity or fracture models. What we study is this one, so we can cancel out inertia, we can cancel out viscous term, and here you see you don't even have an epsilon, so the rate disappears, and this is thanks to the fact that the system are rate independent. So this is what we would like to get at the end. So this is the quasi-static problem that we would like to get. Okay, so now second part, why can we neglect inertia? As I told you before, the first and very good answer is that it's accordance with reality. So experimentally, that it is okay, and it's not surprising. I mean, coders are the imagination, the slow system for excellence. So the slow limit idea, this sounds good. Okay, can we do it in a slightly more proper way? Yes. In modeling, the main tool, if you want to see that one term is small compared to the others, is usually to do a non-dimensionalization. So we rescale the system, we make explicit of the dimension of the system, so the characteristic time scale, so the period of the actuation, the characteristic length, so how much, for instance, the systems move during a period or other stuff. And then we group these all these characteristic dimension in some few relevant constant. This is something it's maybe not done so often in mechanics. You surely can see it more often in pseudodynamics. And probably you've seen at least for Navier-Stokes equation, where you usually do all this rescaling. So you see you rescale time compared to characteristic time scale, and to compared to characteristic length scale, etc., etc. And you find this very important ratio that is Reynolds number. And this comes again, it's again important in locomotion. So you can compute the Reynolds number, for instance. It measures the ratio basically between the viscosity of the fluid, okay, the opposite, the inertial forces against the viscosity of inertial forces of the fluids against the viscosity of the fluid. So if you swim, the the liquid fluid property are more important than property. You can compute for a man swimming, you get about something on the order of 10 to the 6. So for man swimming, inertial forces are very important. If you work for bacteria swimming, Reynolds number is very small. It's 10 to the minus 6. So you can neglect inertia of the fluid, and so throw away all this first part of the equation. That is the fluidodynamics version of what we would like to do for our system. Okay. It's something quite well known also for the study of animal locomotion. And this goes back with some work, especially by Robert McNeill Alexander, that working in analogy with fluidodynamics introduced what he calls fluid number. That is direction. Okay, it started again as probably should be another non-dimensional number from fluidodynamics describing again the reaction between um, inertial forces and some external forces, usually gravitational forces. And again, we can use it also for other systems. So number usually describes, and you can compute it for other stuff. For instance, man walking. Usually, the cells is that of an inverted pendulum, so you can measure the inertial forces, so the inertia of your mass that is up here, the gravitational forces. You get something like that. So the ratio between the square of the characteristic speed of the mass divided with the gravitational constant and the length of the pendulum. And again, scale is something very important if you study animal locomotion, and because scale, usually scale, it's very important to see how this property scales with size. So here you see through the numbers, so the relation between inertial forces and gravitational forces relates very well, changes species with the relative strength end. That is the ratio described. And so also you can ask how much is relevant inertia in humans. For instance, human speaking, human walking are these two white dots here, so about 0.2. The transition in human from walking to running is about 0.5, and here you see some point for running. But you see it's something very consistent for very animals. So even horses, kangaroos, cats. You can compute many animals something very consistent. And so inertia, studying how much inertia is important is also how you distinguish gait. How can you say if one animal is walking or running? Usually you can identify them by looking at how inertial forces are relevant. This is quite useful. For instance, the classical problem for the first walking robot, see them, they walk really, really slowly, and they are essentially quasi-static. And this, you can compute them, they have a foot number like here, so very, very small. And this is because a quasi-static walking robot is much, much easier to control. You don't have the risk to fall down. And this is something, if you want to look on how good is a walking robot, look how much inertia is relevant. This could be a nice principle. Okay, so we can do the same thing for crawlers. Again, usually in literature is called again through the number. There are many ways. Some people consider again the relation between gravitational forces, because dry friction you can see as a friction coefficient times the gravitational force if your crawler is moving above the ground. But your crawler can also crawl inside a tube, so maybe the normal force is not coming just for gravity, but also from the pressure against the tube. So what makes really sense to measure is to measure the ratio between inertial forces and dry friction forces. And this is what we actually get if we make a full non-dimensionalization of our system. This is the coefficient that we get in front of the inertial term. So, okay, Fourier crawlers, is the fluid number small? Yes, it is small. One can do some computation. Um, Usually, then curiously, then perhaps in all cases, I try to do around 10 to the minus 3. That is not extremely small, but quite small, and again, our models are very, very simple. So it's quite good. This happens for the earthworms. It happens for rectilinear locomotion in snakes. Snakes have several ways to move. One that is probably not the most known is rectilinear locomotion, so they can really move straight with compression waves like earthworm likes essentially. This is also the more quasi-static of the locomotion strategy in snakes. If you, again, we get a food number equal to around 10 to the minus 3. If you go look at the classical snake strategy, so slithering locomotion, dual tree locomotion, about 10 to the minus 2, maybe also a little more. So also for snakes going straight, it's good. For some robot, I found all the full data to compute it for two of the quite old one and quite slow one, and we are again about 10 to the minus 3. I still haven't done the computation for some of the fastest one, but I spoke with one of the people working in that with them producing this very fast crawler, the Improm one I showed you before, and he also had some doubt that maybe quasi-static approximation is not working very, very well. So keep in mind, quasi-static approximation good for animals, good for some robots, maybe not all robots. Okay, so you probably now are convinced that the coefficient in front of the inertia is actually small. Okay, how can we pass to something small to zero? The best way to do it mathematically is, again, as I showed you before, with a slow actuation limit. So instead of rescaling everything to a non-dimensional system, there is one parameter that is really important if we want to reach a limit situation, that is the actuation time scale. You cannot change mass. In the case of the glass, you cannot change the shape of the glass. I mean, you can change it a couple of times. It's important if I have a flute or a very flat ball, clearly the speed to the efficiency of quasi-static approximation with the same actuation speed changes. But what you can really, and this is changes the time scale. So what we do is, as I told you before, we just reparameter, we just rescale time, and we do as you told me before. So we keep the dependence on time of the dissipation or of inertia in the same time scale. So we slow down the input and look at what happens. We rescale to a time variable that is of the same time scale of the equation. And what we get is we can carry in front of the term of this epsilon term. So in front of inertia, we have an epsilon square term that comes from the second derivative. With viscous friction, we have one epsilon only because we have a first derivative. Here we see the relevant of dry friction and its peculiarity as a friction. You probably know that I told you before, the system with only dry friction or one homogeneous dissipation potential, and positive with the homogeneous dissipation potential, and energies are usually called rate independent. And this is because the dissipation is rate independent. So if you put an epsilon here, you get exactly the same term. So again, rescale, so we can simply cancel out the epsilon, leaving the derivative. And this is why dry friction is very different from viscous friction managing inertia. So this is our dynamic problem. We put some initial condition on state and initial velocity. And here we pass finally to the theorem. As expected, so we can consider a family of solution of the dynamic problem. We assume that the initial speed actually rescaled converges to zero, or okay, we can take in way bounded. the initial position we convert to an initial position x on 0. And okay, up to a subsequence, this solution, dynamic solution, converges to an absolutely continuous function. This function is a solution of the quasistatic problem with the desired initial condition. And this convergence is uniform on compact times. So for periodic behavior, you can think uniform in the period. This is quite good, and this, as we will see later, it is optimal. We can also see that our other properties here are well preserved. So for instance, dissipated energy is passed to the limit. So the energy dissipated by the dynamic solutions in a specific time interval is equal to the energy dissipated by in the quasi-static evolution in that time interval. We have convergent up to a subsequence, clearly as classical in analysis. If you know that the quasi-static problem has a unique solution, the whole sequence converges. Okay, so let me show you the theorem a little more. So this is what we could expect. So it is good. The solution of the dynamic problem converged to the solution of the quasi-static problem. This is what we wanted to prove. Now, what hypothesis on the energy and on the dissipation potential? I'll give you a very simple example. And let me first look more precisely what happens in the energy. As I told you before, in the quadratic case, the energy is not positive definite, but only semi-definite. And this is because the energy does not really, it's not coercive on all, in this case, for components, but depends only on these three differences, x2 minus x1, x3 minus x2, and x4 minus x3, that we can call with a vector z or a subset space z that is have a smaller dimension that it describe shape. So it does not depend on the state, but just on the shape of the crawler. And so we can actually properly define an energy that depends only on the shape of the crawler, and then we add the invariance with respect to translation. And if you look at this, you can do the same for a continuous model. And so something more closer to what you usually do in continuum mechanics. And in that case, what you get is that our system has no Dirichlet boundary condition. Usually in a continuum mechanical problem, you use Dirichlet boundary condition to pass to a subspace where the energy is coercive. Here, you cannot do that any longer. I mean, if you think a Dirichlet condition means that you are holding in your hand a part of your mechanical body. For a locomotor, so you cannot do that. So the crawler is moving along by itself. Okay, so this is something we have to keep in mind when we define properly the condition for energy. So again, we introduce this general projection to the shape, and we say we will give the property on the energy depending just on the shape. And this is something very classical, very easy. So absolutely continuity in time, uniformly convexity with respect just to the shape, keep in mind. So you have invariance in one direction and uniformly convexity in the other one. Then some very mild regularity, so differentiability and continuous differential in space, and some very simple, very basic and quite normal local control on the derivative with respect to time. Again, if you want also for the regularity of the solution, you can also either require the quadraticity that give all the one before, or also some additional. I won't go into detail. It's usually you see something very, very, very mild and some local estimate on the time derivative of the energy. So you can have variable behavior locally of the energy, but something very, very mild. Of course, what you can do is simply take the projection to the shape as the identity and actually work, apply the theorem also to the case where the energy is actually uniformly convex. So the non-locomotion case, and a simple example, if a geological model. So here you have a chain, again, in a sense, a chain of blocks, but one end of the chain is fixed. Instead of dry friction, here we put here some Venant elements. That means that basically the point of the arrow has dry friction resistance. You can put an external forces. Structure of the friction dissipation in concrete is slightly different, but the general framework is the same. What can we do with dissipation? As I told you before, something quite classical for weight-independent systems. So the potential is convex, positively homogeneous of degree 1 and 0 in the origin. If you have worked with elastoplasticity or other application of weight-independent systems, like usual. You have also some bounds. The upper bounds here is actually gratis because you get it from convexity. You get continuity since we are in finite dimensional. So this one is for free. This bound below, given that we have continuity, implies that the dissipation is zero only in zero. So if you're moving, you have some dissipation, and this is quite good for crawling application. And as you told, you might be less used to consider time dependence of the dissipation potential. Here you have a natural way to define absolute continuity clearly. It has to scale with the fact that it's positively homogeneous with degree 1. There is something else you can do with the dissipation potential, and this is due to the fact that with this low input limit, there are other things that might survive. As you see, viscosity disappears, rate independent dissipation survive. Terms that does not depend on the rate, like energy or something that rescales with the rate, survive. There is another thing that survive, and it is constrained. And in this case, we did our theorem also considering constraint on the velocity. This is equal to assume that the dissipation potential is a dissipation potential as in the previous slide in a closed convex cone and plus infinity outside the cone. Um, if you are in the locomotion model, you have some very mild conditions, structural condition on the cone K, but for application they are always true. What is the relevance of velocity constraint? If you consider a system not moving in 1D, but moving on a plane, this allows you to have a discontinuity in dissipation. So a constraint means I cannot go backward, so I can move sideways, and then if I change my moving angle slightly backward, I cannot do it anymore. So this way allows you to have a convex potential that is not continuous when you jump to the. So you can add something quantitatively different. Okay, key point of the proof. The key point of the proof, how do we prove this theorem, is the concept of energetic solution. Again, something quite standard in mathematics. If you want to solve a problem, you look for weaker form of solution. And in this case, we have energetic solution that are quite classical for the theory of weight-independent system. And they are defined for Bivu function, bounded variation function. In this case, again, it's not properly bounded variation, but you weight the variation with the dissipation potential. So it's something that topologically is basically the same. It is changing. You have to keep in mind that for our cases, the dissipation potential is changing in time. So also this metric which you use to compute the variation depends in time, but with all the assumption we have, everything goes quite nice and quite usual. One has to verify everything, but there are no surprise. And again, as you see, the differential solution can be generalized with this energetic solution consisting of a global stability condition and a weak energy balance. And as you see, we no longer have the subdifferential of the dissipation potential or or the gradient on air energy indices. So we have a weaker solution that, as I said before, works also for BV function. The structure, again, is quite classical. So you obtain some a priori estimate on the dynamic solution. It is not classical in the sense that our dynamic problem are quite unusual. So we cannot use the coercivity on the energy or uniform convexity on the energy. And we have to work more with dissipation. So there is quite a lot of work to do to energy to get a priori estimates. Once you have a priori estimates, you apply a selection theorem, you obtain a subsequence converging to some function x bar in BV, BVR. You prove that that the function is an energetic solution, and again, an energetic solution can be extended to the dynamic problem. Is that you see something that looks like it passed nicely to the limit. And then you recover regularity, so you can show that if it is an energetic solution, it is actually a differential. Okay. Have someone else tried to do that for system with rate-independent friction? Of course, yes. You have several applications that have been considered: viscoelastoplasticity, the bonding, the lamination, damage, or also viscoelasticity with in a more abstract context. There is a very big difference between all this application and our application, and it is that in all other application there is a decomposition of the problem. So you have inertia interacts with elasticity, and dissipation interacts with elasticity. And you can see the comparison in a very simple example. So our system, this is the 1D, one mass version of the rheological model I showed you before. You have in the dynamic problem the inertia, the dissipation, and the elasticity, and in this case, the elastic force that all apply to the same variable. In the other case, more close to classical result, you basically need another variable to describe the system. So you have the position of the mass, and this is essentially you can think as the plastic deformation. This is the total deformation, this is the plastic deformation. And in this case, you see that you have one equation for x that accounts only for inertia. The only forces acting is inertia, the elastic force of the springs and the external force. And to study P, you have to study the viscous, the friction resistance of the Sambenon element and the elastic resistance forces of the spring. So as you see, you have two equations, one variable less, and inertia never interacts with friction directly. I don't say it is easier or more difficult, it is qualitatively different. And this is something similar also happens if you consider continuous model for crawlers. If you look at a continuous crawler, so a strip of an elastic active material, you get that M is no longer invertible. In a sense, our application and also structure of the proof is closer to just vanishing inertia and viscosity results. So the same result, but without the rate-independent dissipation. And of course, in this case, you just have the energy at the limit. There is some nice result, especially a recent one by Chile Solombrino that is quite general. Again, the previous work are mostly in infinite dimension, with exception probably just of this one by Milpe Petrov Martins. This vanishing, inertia, and viscosity are all done in finite dimension. There are two differences with our problem. One is that they need viscosity, so they need that the viscosity matrix is symmetric and positive, definite. We do not need for our result viscosity because we already have friction to use in a way. And they can be worked with non-convex energy, but requiring other strong property like convexivity and energy. Don't go in the details. So there are many similarities. There are also some differences. Okay, I'll ask the final remarks. Okay, can we improve infinity convergence? No. One can build very simple 1D problem where the dynamic solution have the structure you see below on the right. And here, this is basically the classical example for uniform convergence with no convergence on the derivative. And you see here in the picture, so you have this relation that scales homothetically. You convert clearly in infinity to the bisetrix of the quadrant, but you cannot get something more that's infinity convergence. And final consideration, uniqueness of solution. As I told you before, to have a convergence of the whole sequence, you need uniqueness of solution for the quasistatic problem. This is something well known again in the classical study when the energy is coercive. And so you can have, it's sufficient, for instance, for the energy to be C3 if R does not depend on time. The case with R dependent on time is been treated, I think, only in one work, except something I done on locomotion by Heide Milke. And they prove uniqueness of solution in just in the case where the energy is quadratic, again coercive, so positive definite, and without constraint in the of without velocity constraint and with Lipschitz continuity in the time dependence of the quadratic energy functional. This is was for the uniformly convex energy. If we pass to the general case of the locomotion case, this is something I was doing actually when I was in Lisbon. One can have this condition. It's basically to say that the dissipation potential have a unique minimizer if you look at section in the direction of translation. So you restrict to direction that are parallel to the invariance of the direction in which the energy is invariant. So they're orthogonal of Z. And in that direction, the dissipation of energy has a unique minimum. You can find also other characterization, but that would require some more notation. Does it work? Yes, it usually works for concrete applications. For Korean application in infinite dimension, it's something that's probably even easier. There are simple counterexamples. And this is again with very, very simple. You consider the system with two blocks or two contact points, just expansive of contracting. If you recall, the crawlers can do several stuff. They are friction anisotropy. I'm almost finished. Last slide. Or the control friction. If you have isotropic friction and constant, you have a multiplicity of solution. You can see either one block move or the other blocks move. It is not something the crawler does. One can find also that it is stupid for locomotion. This is something that we wanted to prove. We're still not able to. So to use with vanishing inertial limit as selection principle for the case of multiplicity solution. What I expect if you get something like conservation of momentum that should show that with this multiplicity of solution, you cannot really use them to move. This if you don't do strange things with viscosity. Okay, other open problems, clearly we use a Harris selection principle, so we know that the subsequence or sequence converges. We don't know how fast, so we don't know if 10 to the minus 3 is actually very small. This is something we would like to do. And there, of course, one can hope to do the same also for higher dimensional model. Okay, this was my last slide. If Nicolas allows me, let me also do some advertisement for a small workshop we are organizing online on the 23 March. It is a nonlinear meeting 2021. It is the 6th edition of a meeting we previously had with other organizers physically in Milan, in Turin, in Udine. This year its line is in the afternoons. I think 2:30 Portuguese time is Monday and a Tuesday, so no overlapping with this seminar. And if you're interested, maybe later I can copy the link on that. Thank you.
Yes,